we're reviewing Unit 4, Position, Velocity, and Acceleration today. So Unit 4 includes some basic formulas that we've previously used. We're going to look at average velocity. Remember, the word average is the same as average from back in the day, where you're going to sum everything up top and then divide it by the change in the bottom. So for average velocity, it's the change in position over the change in time, where x of t plus delta p is the end position minus x of t, which is your initial position, all over delta t. Typically, we're going to talk about motion in a straight line, meaning we're moving along the x-axis. So our position is x as a function of t. Now, instantaneous is the calculus version of this. Instantaneous velocity of an object is the derivative of that object at the particular point. The derivative of that object at its point is known as v of t, or x prime t. And then the last thing you need to recall is that speed is the absolute value of velocity. So speed is absolute value of v of t, or absolute value of d of x over d of t. Acceleration is the second derivative of position, or simply the derivative of velocity. We say a of t equals v prime t, or x double prime of t. And we can also integrate velocity to get position, and we can integrate acceleration to get velocity. So this is the working backwards version of position, velocity, and acceleration. So an important concept is speeding up or slowing down. Speeding up or slowing down is when the velocity and acceleration either have the same sign, meaning both are positive or both are negative. Therefore, the speed is increasing. If an object's velocity is 40 miles per hour and the object accelerates 10 miles per hour, then the object is speeding up because both positions, velocity and accelerations, are positive. If the velocity and acceleration are in opposite directions, meaning one is positive and the other negative, such as the speed is decreasing, an object's velocity might be positive, but its acceleration is negative, therefore making it negative or slowing down. So we have a lot of givens. The AP exam, again, is going to be entirely open-ended for your response. They're going to give you terminology and definitions that are going to make you think critically. So you're going to see the word initially. Initially means that t equals 0. At rest. At rest implies that the velocity is 0. At the origin, that x of t is equal to 0, it means we are starting at 0, 0. Velocity is positive. This tells you the particle is moving right. Another way of talking about that is saying up. Velocity is negative. A particle is moving down or to the left. Average velocity is change in position divided by change in time. If you're asking or looking for average velocity, you're talking about x of t. Average velocity given v of t means that we are taking the average value of the velocity function, meaning you are working backwards. Instantaneous velocity is velocity at any given moment. Instantaneous is v of whatever we are looking for. A positive acceleration means velocity is increasing. A negative acceleration, velocity is decreasing. And again, we talked about speed being the absolute value, and total distance is actually the integral of speed, or the integral of the absolute value of velocity. So one of the things I want to do is look at a position, velocity, acceleration free response question. This came from an AP exam probably about 10 years ago. It was a non-calculator, which again, this year's AP exam is focused primarily on non-calculators. So I wanted to look at this and talk about a non-calculator position, velocity, acceleration. So at this point, we've learned integration as well as differentiation. So this is going to involve integrals and derivatives. So it says a particle is moving along the x-axis. So we're given the graph of velocity, and the particle is moving along the x-axis. So the velocity at time t equals 0 to 6 is given by a differentiable function, which means that we can find the acceleration, whose graph is shown above. The velocity at 0 is 0. So at time t0, the velocity is 0. At time t3, the velocity is also 0. And at 5, the velocity is 0. So why does the velocity being 0 matter? Well, if the velocity is at 0, then we know from the previous page of information, if the velocity is at 0, then the particle is at rest. So the particle is not moving at 0, 3, and 5. We're also given that the graph has a horizontal tangent at 1 and 4. The areas of the regions bounded by the t-axis and the graph is given by 0, 3, 3, 5, 5, 6, are 8, 3, and 2. So what that means is that the area under the curve, or between the curve and the axis here, is 8. The area above is 3. And then again, the area from 5 to 6 is 2. So you have 8, 3, and 2. And at time t equals 0, the particle is at x equals -2. So what does that mean? Well, that means that at x of 0, the y value is -2. That's kind of like your initial condition, or your starting point. So part A says from 0 to 6, find both the time and the position of the particle when the particle is farthest to the left. So what that means is we need to find points at which the particle is moving. So x equals 0, the position is -2. The next position of concern is going to be the 0 on the graph, which is 3. So we know we're going to do position in red. X of 0 is -2. X of 3 is -2 plus the movement from 0 to 3, which is the antiderivative of velocity, which is the area of the curve. So it's -2 plus a -8 because it's below, so it's going backwards, which means at 3 seconds, the particle is 10 units to the left. Then we're going to look at x sub 5. So again, now you take into account that initial or the position at the next point. So you could either do -2 plus the integral from 0 to 5, or you could do -10 plus the integral from 3 to 5. Either way, you're going to get -2 plus -8 plus 3, or -10 plus 3, which gives you -9. And then the last position we are going to consider or look at is x sub 6. So again, it's either the integral from 0 to 6, or our last position there, plus 5 to 6, which would be -9 minus 2, which is -11. Oh, just kidding. Yeah. -10 plus 3 is totally -7. And -7 plus -2 is -9. So it asked me, when is the particle furthest to the left? Well, left would be our negatives. So it's at -2, -10, -7, and -9. The number furthest to the left, in this case, is -10. So when is the particle furthest to the left? The particle is furthest to the left at t equals 3, when the position is x sub 3 of -10. And my justification for that is actually all the work we just showed. So the answer is at t equals 3 when the position is x of 3 equals -10. The justification is the candidate's test up above. Okay, the part B says, for how many values of t from 0 to 6 is the particle at x equals -8? Explain your reasoning. Well, we know that the particle is moving continuously, so this is going to be an intermediate value theorem, because essentially what we're testing for is range values. So we know that at 3, it's at -10. We know that at 0, it's at -2. So again, we're kind of just taking that into account. So I'm going to draw on this graph. At 0, we're at -2. At 3, you're down here, and we'll say that's -10. At 6, you're at -9. And we said at 5, we were at -7. So the position graph is going to kind of go somewhere down, up, and then back down. So this up here is -7. This is -9, -10. So it says, when is the particle at -8? So -8 would be in here between -7 and -9. And that's going to occur once, twice, 3 times. And we know that because of IVT. So by IVT, there are 3 values of t for which the particle is x equals -8. To justify, you would just say by IVT, x of t equals -8 3 times. on the interval from 2 to 3, is the speed of the particle increasing or decreasing? Give a reason for your answer. So we have to talk about the fact that speed is the absolute value of velocity. So essentially it's like looking at this graph entirely on a positive nature. So that would be kind of like the green function I just drew in. So speed and velocity have to do with the sign of the function. So from 2 to 3, the sign is positive. However, the function is decreasing. Therefore, the speed is decreasing because this function we have is velocity. So the idea is that if you look at the original graph given, you're going to be like, oh, velocity is increasing from 2 to 3, therefore it's positive and increasing. But it's not, because we're talking about the absolute value of speed, which is up there in green. So since the absolute value of speed is actually decreasing from 2 to 3, so on the interval from 2 to 3, the velocity is negative and the velocity is increasing. So that's another way to talk about speed, or you can just think of the absolute value. So if you want to talk about it based on speeding up, slowing down, you could say, okay, the velocity at, that time interval from 2 to 3 would be less than 0, therefore negative. Since the velocity is increasing, that implies that acceleration is positive. So opposite signs says decreasing or slowing down. Or again, looking at the graph of the absolute value of velocity from 2 to 3 is decreasing. Therefore, speed is decreasing. So 2 ways to ultimately get to that same answer. And then during what time intervals, if any, is the acceleration of the particle negative? So the acceleration will be negative when velocity is decreasing. So acceleration is negative if velocity is decreasing. Well, we're given the graph of velocity up there. So it's decreasing from 4 to, looks like, negative infinity, or if we're talking about a closed interval, 6. And then from 0 to 1. The acceleration is negative on the intervals 0 to 1 and 4 to 6 because velocity is decreasing. The last thing that's part of the PVA is basically talking about local linearity. This is part of Unit 4. We want to talk about under and over approximations for our tangent lines. So again, tangent line y minus y sub 0 equals mx minus x sub 0, where we can predict a complicated point for a not so complicated formula. So what we're going to do here is look at the function f of x equals the square root of x, and we're going to approximate 25.2 without using a calculator, given that, we want to basically use a point that's nice near there. So what we're going to do is we're going to look at f of 25, which is really close to 25.2. And we know that the square root of 25 is 5. So this is kind of like my x sub 0, y sub 0. And then we're going to look at the derivative, which is 1/2 x to the negative 1/2, or 1 over 2 square roots of x. And we're going to look at the derivative at that nice point. Which is 1/10. So that represents the slope of the tangent line. And then what we're going to do is we're going to linearly approximate 25.2. So linear approximation is L of x equals f of a plus f prime of a at x minus a. And in this case, our x is 25.2. So f of a, so my a is kind of like my x naught. My f of a is my y naught. So my y naught is 5 plus the slope at 5, which is 1/10, times 25.2, which is my x, minus my a, which is 25. So I get 5 plus 1/10 times 25.2 minus 25. So that's 0.2. But we know that 0.2 is really 2/10. So we end up with 5 plus 2 1/100ths, which is really just kind of like saying 1/50th, which is 0.02. So it would be 5 and 1/50th, or 5.02. If it asked you for the equation of the tangent line and not the approximation of it, then the equation of the tangent line would be y minus 5 equals 1/10 x minus 25. You could also add that 5 over if you want. But again, this right here represents the equation of the tangent line. This is the approximation of 25.2. Would 25.2 be an over or an under approximation? So if you think about the square root of x function, it would look like this. We're talking about the point 25.5. So it's way out here. So is that graph concave up or concave down? Well, the graph is definitely concave down. So if you go back to your chart, if the graph is concave down and the line is above, then it's going to be an over approximation. It would be an under if it is concave down and decreasing. So this is an over approximation.